Great. Thanks, Hannah. Thank you all for coming. It's a pleasure to join everyone. As Hannah said, I'm going to talk about multiplicative uniqueness of rational equivariant K-theory. Let me start by saying this work is joint with Christy Hazel, Jocelyn Ishak, Magdalena Kedgerik, and Clover May. So I want to start by just sort of reminding you of some things about equivariant topological K-theory, which is our main object of study, before telling you about the uniqueness results and then giving a bit of a sketch of how we prove this. So that's the plan. So equivariant topological complex K-theory, this is our primary object of focus here. As you might recall, topological K-theory is one of the motivating examples of spectra, like full stop. Very, very classical thing. And it's also one of the earliest known examples of an equivariant spectrum, so an equivariant cohomology theory. And work of Siegel naturally shows that your standard definitions of topological K-theory have a good equivariant extension, where instead of working with vector bundles, you work with equivariant vector bundles. And so in particular, if you want to look at the K-theory of a point, well, that should be vector bundles over a point. And well, that's just, a vector space with an action of your favorite group G. So this is really just representations. So the K-theory of a point, in degree 0 at any rate, it's built out of, I guess I'm missing my bot periodicity class. Let's add that there, should be giving us the representation ring of our group G. And of course you have tensor product and you have Whitney sum of vector bundles. And these, just as in the non-equivariant case, these produce a commutative ring structure on equivariant complex K-theory. And so that's the multiplicativity in the title. So if we go back to the non-equivariant case, then if work of Baker and Richter shows us that the E infinity ring structure that you have on non-equivariant K-theory, this is unique. And they do this by an obstruction theory argument. This is one of many examples they're interested in. And so then in the equivariant case, we could try to ask a similar question, like what does, how unique is the E infinity ring structure that you have on equivariant topological complex K-theory? Now, when you want to talk about multiplicative structure in the equivariant context, especially commutative multiplicative structure, you run into the fact that there's actually, you might mean various different things. There's a number of different levels of equivariant commutativity. These are encoded by what are known as N-infinity operads, recently analyzed in great detail by Blumberg and Hill. And there's sort of like a hierarchy of levels of structure. Commutative multiplicative structure corresponds to how much you want to require your E infinity multiplication be compatible with your group action, like how homotopically coherent those things are. And the strictest of these levels is called genuine commutative structure. And it's, we might say that this is encoded by an operad, which I'll call E infinity G. The G is for the group action, but you could also think of it as for genuine. This is the strictest level you can have. This corresponds to having lots of norm maps, if you want to think about it that way. And then the least strict is what is known as just, this E infinity structure or naive commutative structure. And the difference here is that the weakest structure, the weakest structure corresponds to just taking your favorite E infinity operad with no group action and saying, well, I could give that as a trivial group action and it's still an E infinity operad and it can act in G spaces and ask about algebras over that. And in the stricter case, you have to incorporate the group action on your E infinity operad in a much, much stronger way. So that's the difference. And equivariant K-theory, so KUG, this sits up here and it's at this highest level. And this is one way to see this is Mikael Joachim has a beautiful construction of equivariant complex K-theory that shows it's rigid as you like. So it sits there. Of course, there's a forgetful functor. So if we have the strictest structure, we could also forget down and relax what we're remembering and think about it as having the least strict functor. And so then the question is, how unique is this structure that we have? And the answer, well, the answer is we don't know entirely, but the answer is, at least in part, well, this is pretty complicated. And so maybe we want to simplify a little bit and see if we can answer that question first. So we will answer that question. So since the algebra is complicated, we can apply a standard, tool from homotopy theory or calculational homotopy theory from way back and say like, well, let's rationalize. Stuff must be simpler. And so we do, and then we can prove the following result. So if you have a finite abelian group, and you look at a rational spectrum that has this genuine commutative structure, so it's the highest level of structure, and it's homotopy groups, it's the homotopy green functor, so it's homotopy groups with their ring structure, but just at the level of homotopy, that's the same as what you have from equivariant complex K theory, then you get a zigzag of weak equivalences of genuine commutative ring spectra between X and the rationalization of KU. So this is the weak equivalences of genuine commutative ring spectra. Okay, so that's the basic results you can get. And so in this sense, you have uniqueness of this genuine multiplicative structure. Anytime you have any spectrum, all you need to know is that the underlying homotopy groups are the same as what you had for KU. They have to be equivalent in the sense that there's a zigzag of weak equivalences between them. So this is a cool result. I think it's neat. I also want to think about it not just because I'm interested in K theory, but also I think about this result as giving us a little bit of an exploration of what the heck genuine commutative ring structure is about. So this is an exploration of genuine commutative ring structure, as well as being a nice result to have about K theory. So there's sort of two ways of viewing why you might be interested in this kind of a result. This result stands in contrast with another theorem that we prove, which is about what if I don't take periodic complex K theory, but instead I take connective complex K theory. And in that case, you can find rational genuine commutative ring spectra that are equivalent to little ku, rational little ku of G, as naive ring spectra, but they're not equivalent as genuine ring spectra. So in particular, the fact that they're equivalent at the weakest sense, the naive sense, it implies, of course, that their homotopy groups are the same, but you don't have an equivalence of genuine ring spectra. So you have a difference here between like the level of rigidity or the strictness of these kinds of equivalences, of course, coming with the strictness of the algebraic structure. I mean, maybe you should think that the second result is not that surprising when we're, passing from naive ring spectra to genuine ring spectra. We're asking for significantly more algebraic structure. So we're increasing algebraic structure. And, as a general rule, you should think that increasing algebraic structure should correspond to making it harder for things to be equivalent, right? So this should make things harder to be equivalent. And that's what we're seeing here in the connective case. And the point is that it's maybe therefore a little bit surprising that in the periodic case, you increase the algebraic structure and it's no harder to be equivalent. This is maybe the more surprising result. I should also mention that, in fact, we have the kind of uniqueness result I stated for KU as a periodic KU as a genuine commutative ring spectrum above, we have that same kind of uniqueness result for both periodic and connective K theory at the naive level. So these are both unique as naive commutative ring spectra. And so we have the same results for both of these spectra at the naive level, and then there's this distinction at the genuine level where I have uniqueness for the periodic case and not for the connective case. Okay, so those are the main results I want to tell you about. Okay. And I think about them, as I said, they tell me something cool about K theory, which who doesn't love K theory? And then they also tell me something fun about how do norm maps, how does genuine commutative ring structure work in the equivariant case? I see that Bob is asking, connective equivariant K theory, what do I mean? I mean connective in the simplest case. I mean it has no homotopy groups in degree less than 0. So I just kill them. It's yeah, thanks, Bob. All right, more questions. Okay, so let me tell you a little bit about how we prove these results. And the main proof technique comes from the fact that we're rationalizing. So as I said, rationalization really simplifies a lot of homotopy theory. And in particular, after rationalization, we have algebraic models for the categories of genuine and for the categories of naive commutative ring spectra. So we can turn our problem that's about spectra, which are, kind of complicated, into a problem that's purely algebraic, and it's about commutative differential graded algebras, but they're commutative differential graded algebras with a lot of structure, which is, the trade-off you get. So how do these work exactly? So first, let's think about what's happening non-equivariantly. We'll remind ourselves what's going on here. So non-equivariantly, we know that there's equivalence between the category of rational spectra and the category of chain complexes over Q. And so this is, ultimately, these ideas go back to Sayre at least. But if you want, you can make this a very nice, symmetric monoidal equivalence. And then you can ask about E-infinity algebras in rational spectra. And those you can show are equivalent to commutative differential graded algebras over Q. So you're sort of saying commutative objects on the one side and commutative objects on the other side, they're equivalent. That's what you get. Setting this up right, this is work of Shipley and then of Richter and Shipley to get these kind of nice equivalences, that especially ones that pass to the infinity algebra side. Right, so you can see that, if we wanted to ask this question, kind of questions like this, non-equivariantly, we would be asking questions about the structure of commutative differential graded algebras over Q. What happens when we want to incorporate a group action? So my groups are going to be all finite and mostly abelian, although this particular part doesn't require the abelianness. I'll say a little bit about where that comes in. So if you add a group action and you look at equivariant spectra, then the work of Kedgerick tells you that you can describe this in terms of chain complexes. The rational category of rational G spectra is equivalent to a product over conjugacy classes of the subgroups of G of chain complexes of modules over the group ring of the Weil group of H and G. So here, this is the Weil group, which is the normalizer of H and G, mod H. So you get this nice result that tells you how to encode rational G spectra as algebraic objects. So you just get a bunch of different chain complexes, all of which are CDGAs. And if you work a little bit harder, which Barnes, Greenlease, and Kedgerick did, you can see that you can get an equivalence between the E-infinity algebras in G spectra and commutative DGAs in these group rings. But notice that this is the naive part here. So these are the naive commutative things, which you can tell because I secretly did not put a G on the top. So this is on the left-hand side, I'm looking at algebras over the simplest E-infinity operad with a trivial G action, and that's what you get. So I want to make two observations about this result. So one is that this Weyl group action here, which we're seeing both in the commutative ring object case and just the no ring object case. This comes from a residual action of the Weyl group on, so a residual action on, really we should think about it as on geometric fixed points. And in fact, you know, how to think about these equivalences is that if I have an object X in G spectra, rational G spectra, then this corresponds to some product of DGAs, or I guess product of chain complexes. So I'm going to call those chain complexes like theta sub H of X. That's the one that I get corresponding to the subgroup X. So if this is my name for my correspondence, I don't control exactly what theta sub H is, but I do control its homology. It's a chain complex, so I can ask about its homology. And I know that the homology of theta sub H of X, this is going to be the homotopy groups of the geometric fixed points, the H geometric fixed points of X. So I'm controlling the homology of the chain complexes that come out in terms of the homotopy groups of the geometric fixed points. But I don't control exactly what these theta H's are. And then, you know, then it becomes like, if you believe this, it becomes sort of plausible that like the Weyl group is the sort of thing that should be acting on the chain complexes I get at each level. Okay, so that's the first observation. I have some control over the chain complexes I'm getting in terms of geometric fixed points. And this is where these actions are in some sense coming from. The second observation goes back to this point that I made before, which is that on the left-hand side of the Barnes-Greenlease-Kedgerick equivalence, I have naive commutative ring spectra. And what's happening is that in the algebraic world, so in the algebraic setting, these E-infinity objects, these are strictly commutative algebras. Or strictly commutative objects, because it's you have a chain complex and it's a ring, and it's either a commutative ring or it's not. It's basically what happens. But in G spectra, we have all of these, as I said before, we have all these levels of commutativity, and these E-infinity objects here, these are only the naive commutative ones. And so, this algebraic model, this isn't sort of seeing enough to encode the genuine commutative ring spectra. So you need, I don't know, I call it a more robust algebraic model in order to incorporate this additional structure. So the E-infinity G / genuine structure. So this model the Barnes-Greenlee-Sketcherick one, this is actually one that we can use and do use to prove the results about the naive commutative uniqueness that I mentioned before. But if you want to ask about the genuine commutative uniqueness, you need a stronger model. You need a slightly different one. And fortunately for us, Christian Wimmer constructed such a model for us. This is what it looks like. So if G is a finite group, he proved that the genuine commutative ring spectra, so that's the E infinity G algebras in rational G spectra, there's an equivalence of infinity categories between that and a category of functors from the orbit category, so that's what I'm calling orb G, maybe sometimes I drop the G and just call it orb, to rational CDGAs. So this is actually a very nice generalization of the Barnes-Greenlee-Sketcherick thing. It refines to their result, even though it doesn't quite look like it to begin with. So I first want to explain, like, this is the algebraic model we're going to look at, and I want to explain, what does this actually look like? What does it really mean to have a functor from the orbit category to CDGAs over Q? Okay, so what does the structure look like? Well, first of all, we should think about, like, well, what is the source category? Orb, right? We're taking functors out of orb, so what does it look like? Well, the objects are just orbits, G mod H. And the morphisms are just equivariant maps. So from like G mod K to G mod H. And some of you may have calculated for yourself, maybe in fact time and again, depending, equivariant maps between orbits, these are equivalent to subconjugacy relations between the group you're quotienting out by, so subconjugacy relations, like, you know, let's say K is subconjugate to H, like this. And so using this, you can compute, for example, what are the automorphisms of your favorite object, of your favorite orbit here, G mod H, and you see that these are really just actually the Weyl group, right? Because you're just asking about how can I like conjugate H into itself, and it turns out you can do that by things in the normalizer, and then I don't care about the ones that keep H as itself. Those are the trivial conjugacy. So right, so you get the Weyl group. Because I'm going to be interested in the case where G is abelian, I want to point out that this is actually just equal to G mod H itself when G is abelian, because everything's normal. But it's confusing to have G mod H appearing in both these cases, so we'll probably still call it the Weyl group, even when we know it's simpler here. And so this gives us a little bit of a sense of what this source category looks like, the orbit category. And so then that allows us to understand what a functor out of this into CDGAs, what does this look like? So this reduces to the following data. So I have, for every subgroup corresponding to that orbit, I have a CDGA, which I'll call a dot of H. This is a rational CDGA. And corresponding to the automorphisms of that orbit, I have a Weyl group action here. So this is, I have one of these for each orbit G mod H. And so this is basically where the data of the Barnes-Greenlee-Sketcherick model is coming from. For every subgroup, or every conjugacy class of subgroups, I have a CDGA with an action of the Weyl group. So I have a CDGA over Q adjoin WGH. Okay, so that's the object level data, but of course it's a functor, and so the important data is much of it contained in the maps. So we need to think about the maps, right? So what do we have map-wise? Well, we have a map from our CDGA for K to our CDGA for H here. So this is, say for each inclusion of subgroups, K and H. of course, I have such a map for every subconjugacy relation, but I can take care of the conjugacy part in terms of my Weil group actions, right? Like if I have a subconjugacy relation, I can factor that as like an inclusion and then a conjugacy relation, which is an inclusion and then an action in the Weil group, or in fact, either order. So I have these maps. These have to be, compatible with the actions, which is really just saying that it's functorial. So these are sort of compatible with the actions. I should note that in the case where G is abelian, and all these Weil groups just look like G mod something, I could really think about having a G action on every one of these CDGAs, and then I really am asking for these to be G equivariant maps, and then like, the stabilizer of AH has to include H, things like that. Okay, so these are compatible with the actions. They're maps of CDGAs, because this was a functor to the category of CDGAs. So CDGAs, and so in particular, this means that they're degree 0 maps. When I think about them as maps as chain complexes. And that seems like pretty normal, except that I'm going to tell you that where are these maps coming from? These are what we would like to call the shadows of the norm maps. So if you're familiar with, the whole hierarchy of equivariant ring spectra, you may know that the genuine ones are characterized by having these norm maps. And one thing to notice is that norm maps are not in general maps of degree 0. They have some sort of complicated representation grading shift going on, but it turns out that when you rationalize, you can actually capture all the essential data in these degree 0 maps, which we think of as like the shadows of the actual norms. So this is pretty cool, and like it's like a beautiful part of Wimmer's result that this is all that you need. So these are really nice. Okay, so this is what the algebraic objects that correspond to our rational genuine commutative ring spectra look like. They look like a bunch of CDGAs with actions of Weil groups, and then a bunch of like maps of degree 0 of CDGAs between them. So what are some examples? Well, one example is I can think about like, well, what happens to the sphere spectrum, right? The sphere spectrum, solid example of a genuine commutative ring spectrum. And so this is supposed to give me a functor from the orbit category of G to CDGAs. And what does it do? It takes any orbit, G mod H, and it just maps it to Q, concentrated in degree 0, which is a perfectly pleasant commutative differential graded algebra. And all the maps are the identity. And the identity map commutes with everything you want, so you're in business, right? And you can know this because really what's happening is that like this is taking the unit object to the unit object, and the unit object in the algebraic model is just this like Q everywhere. So so you get that for free from the fact that you have a nice algebraic model. Here's maybe some more interesting examples or more surprising examples. So let's like restrict to the case where G is CP, cyclic of order P, just for simplicity of writing down what these are. So we can get some algebraic objects. I'm writing them so that like this is the thing that corresponds to E. This is the image of CP. This is like A dot of E, A dot CP. Again, here's E and here's CP. And so I'm supposed to have, these CDGAs. I'll just take Q adjoin a polynomial generator at each spot. I can put trivial actions on these. And then I need these ring maps from Q adjoin X to Q adjoin X. And on the one hand, I could take the identity ring map, it's also a perfectly nice ring map, or I could send my polynomial generator to 0. And these give me two different objects in my algebraic model that are not equivalent. And so they correspond to non-equivalent rational genuine commutative ring spectra. So non-equivalent genuine, I'm missing the word rational, which is important here. So rational, genuine CP ring spectra. But if I forget the genuine structure, then I'm not remembering the maps, I'm only remembering the objects. And so these are actually naively equivalent because I can't tell the difference anymore. So that are naively equivalent. So forgetting down from genuine to naive is just forgetting about the maps and only remembering about the CDGAs you have at each spot. It corresponds to restricting to the subcategory of isomorphisms in the orbit category. I have no idea what commutative ring spectra these correspond to, but they're there. Okay. So now let's turn to topological K-theory. And so what are we going to do to try and get at topological K-theory? So here's our strategies. We've got this algebraic model, and we want to understand what happens in the algebraic model. So the first thing we should do is try to understand what is the homology of the image in the algebraic model. That's what we can control via like understanding geometric fixed points. So we want to compute what this is at every subgroup H of G. So here, maybe now from here, we'll like let G be finite abelian. And think about this. So we want to compute the homology values. And then we want to try to show that actually just knowing the homology here like buys us everything. So we need to show that it determines at least up to weak equivalence. First of all, the CDGAs that have this homology. So that's not always the case, right? You can have sometimes non-equivalent CDGAs with the same homology, but in our case, that will turn out not to be true. And also, we need to not just know what the CDGAs are, we need to know what the maps are. So we want to show that actually knowing the homology is enough to determine for us the CDGAs that have these homologies and the maps between them. And that's pretty cool. So, right, well, I guess I restricted to G finite abelian here, but it really is finite abelian, so we're restricting again. So here's what you can compute. So right, as I said, we control the homology by controlling the geometric fixed points of the spectrum and the homotopy groups of these. And so we know what these are. These come from the representation rings of the subgroups we rationalized, and then bought periodicity. This tells us what the homology is, what the geometric fixed points, and therefore what the homology is supposed to be. So we calculate as follows. So for G finite abelian, the homology of the CDGA I get corresponding to a subgroup H is 0 when H is not cyclic, or it's the cyclotomic field extension of order n when H is cyclic of order n, adjoin a bot class and its inverse. So this is a cyclotomic field extension. So basically, it's like the nth roots of unity when H is cyclic of order n. And we expect that rationally, representations should be determined by what happens at cyclic groups. This is like Artin's theorem in representation theory. So it's expected that the cyclic groups are what counts here. It's not a shocker. Benjamin Bohmann has work on that kind of a result from a more topological perspective. And we also know what the action of the Weil groups, which are, as I said, they're G mod H. The Weil group actions are all trivial here. And this is one of the most important cases. This is where abelianness is super important. It's important because making the Weil group actions where they actually come from is the action comes from conjugation action on representation. And conjugation, when you have an abelian group, is trivial. And so that's why when we're looking at an abelian group, we have a trivial action, at least at the level of the homology of our CDGAs. Okay. one really cool thing that comes out of this is that these homology rings are graded fields. And graded fields are great. I mean, fields are great. So what does this buy for us? This buys us the really lovely fact that if I look at, the maps I'm trying to understand on homology, so the map from like the DGA I get at a subgroup K to the DGA I get at the subgroup H, or at least on the homology here, this map, this is injective because it's a map, it's an inclusion of field, it's a map of fields, and maps of fields have to be injective. So this is an injective map because can't have any non-injective maps of fields, except maybe to the zero field. And I mean, I guess here maybe I'm assuming that K and H are both cyclic, so that this is an interesting map. And on degree 0, we know what's going on here is that I'm getting some sort of like Q adjoin a kth root of unity to the cyclotomic field extension, where Q adjoin an nth root of unity here. I'm getting a map of fields like this. So I'm looking at including the smaller roots of unity into the bigger roots of unity. That's what's happening. Okay, so this is in degree 0. So that's really nice. Like, this actually tells us that we really can understand a lot about what's happening here at the level of homology. One thing I want to point out, I'm not going to get into this in detail, but if I'm looking at connective K-theory, then I get almost the same homology groups for my CDGAs, except that I'm just adjoining a bot element and not the inverse of the bot element. Don't have the bot element's not invertible in connective K-theory. And so that means that I no longer get that I definitely have to have graded fields here, right? Like the bot element's not invertible, there's no field. And so I have more flexibility in terms of how I can map the homologies to each other with the same underlying, more flexibility on the maps with the same underlying homology groups. So that's actually like where we can see the difference between the connective and the periodic K-theories that I came up in the theorems I cited earlier. Okay, so here's our step 1. So we calculated the homology of the CDGAs that are corresponding to our periodic complex K-theory. And now we need to try to show that actually that homology, well, we saw it determine the maps on homology, but we need to know that it determines the CDGAs and the maps on the CDGA level. And so what we do is we construct a diagram of CDGAs, what called D, that has what I want to call a loosely initial property. This is not a technical term. So what do I mean? So first of all, I want D to actually have the homology I'm interested in. So it should be at every H, I should get a CDGA whose homology is the same thing as the homology of the CDGA I got from periodic complex K-theory. Okay, and then it should have the additional property that if I have any other functor here, so any other algebraic object in my algebraic model with the same homology as periodic complex K-theory, then I have a natural transformation, a map of functors from my like loosely initial guy D to A that induces an isomorphism on homology. So that's the sense in which I want to say it's loosely initial. So there's no uniqueness condition here, but there's always a map. That's what I'm saying. So right, so what this is telling us is that this implies that any A with this homology is what we might call diagrammatically formal. So in general, one says that like a CDGA or chain complex is formal if it's determined by its homology. So anything with the same homology, any two things with the same homology are connected by a zigzag of weak equivalences. What this result says is that anything with the homology of periodic complex K theory is connected to it by a zigzag of weak equivalences to its homology and to itself. So, for example, let's be quite concrete about how we get the theorem statement from this. So if I have a genuine commutative ring spectrum here, and I know that its homotopy groups are the same thing as the homotopy groups of rational K theory, then that implies that I get the same homology groups for the corresponding algebraic objects in Wimmer's model. And so we have a zigzag that looks like, I take theta of x, and I can map to that from my loosely initial CDGA diagram D. And I can also map to the algebraic object I get for rational equivariant connective K theory. Or sorry, periodic K theory, not connective. So I get this diagram, and this tells me this is, these are weak equivalences. Oh, sorry, this has to be a weak equivalence. Weak equivalence, weak equivalence. So I get my zigzag of weak equivalences. And in fact, it zigs exactly once. So that's what you have to do. So if we can find this D, then we can prove the uniqueness result. We get this zigzag of weak equivalences. So the question is then, how do you hook up such a D with this property? Well, it's easy to find CDGAs whose homology looks like the cyclotomic field extension adjoin a Bott element and its inverse. This is not hard to hook up. You do the following. So you say, okay, I want in degree 0, I want homology. That's the cyclotomic field extension. So how am I going to do that? Well, the cyclotomic field extension, I can view it as like a polynomial algebra divided by the cyclotomic, truncated quotient out by the cyclotomic polynomial. So I'll do a polynomial algebra in degree 0, x in degree 0, and I'll tensor with an exterior algebra, and I'll impose a condition that the differential on the exterior class in degree 1 is the nth cyclotomic polynomial on x, right? So this will give me Q adjoin zeta n. And then I can tensor with something that will give me like beta Q adjoin beta inverse. So I'll have class, maybe I'll call gamma bar, and tensor with another exterior class, and d of y will be equal to gamma times gamma bar minus 1. So here, if I do this, then in homology, the class of x represents a primitive nth root of unity. Okay, so if I just wanted to realize one of these CDGAs by itself, it's easy to do. But the difficulty is that if I look at a map from Q adjoin the pth roots of unity to Q adjoin, say, the pth squares roots of unity, I have some generator, if I pick a generator here, which is what I'm doing when I build my CDGA as above. So this generator, it goes to some pth root of unity, but it might not go to a pth power of some chosen generator that I had already before. But maybe not the pth power of a chosen, zeta p squared. It goes to some pth root of unity, but I don't know which one in terms of my zeta p squared, right? Somehow I think of this very, I have my favorite primitive pth root of unity, but I'm just biased, and maybe this map does not have it share my favorite pth root of unity, So the solution is that, you have to make all the possible choices. You have to find, if you want to have room to have this sort of initialness type mapping property on those maps, you have to add the ability to have a free choice of p to the nth roots of unity for every p and every n. And the way that you do that is as follows. So I'm just gonna, maybe I'll just mostly tell you what happens when H is cyclic, what chain complex you choose, what CDGA you choose. So you do the following thing. you look at all the primes, dividing the order of H. And then for each of these primes, you're going to look at all the subgroups that are cyclic of that power order and that are not trivial. You don't need the trivial group. And for each of these, you add a generator, which is going to be like the p to whatever that power is, root of unity. And I'm going to index them on the subgroup itself. So I add these guys, and then I'm going to tensor with the same thing to add the bot class. The bot class is easy. And what are my differentials here? The differential on the exterior class corresponding to a subgroup K is equal to either the p cyclotomic polynomial on the corresponding polynomial class when K is actually a p cyclic group for like the actual prime, and it's the difference between the polynomial class 1 degree, like one subgroup down, the p power here. This is, if K is Cp to the n, and K prime is the maximal proper subgroup here. So the maximal proper subgroup is really just a cyclic group of like one smaller power. And so I'm twisting them, and then I'm twisting them together. So this is telling me that this gives me room to say like, well, the whatever generator I chose for like K prime is going to some root of something, but it's not necessarily like a specific one. So you can check that this construction gives you the right homology. It's not that hard to show. It's just like a regular sequence argument. And then the maps that you need between these for different, H's and H primes, really all I do is I just take generators to the generator with the same name. That's what my map does. It's like very nicely set up. So the map just takes from like dk to dh, just takes generators to the like name generators. And then you have to show that this provides you with enough flexibility that you can map into any diagram of CDGAs that has the appropriate homology. And all you need to know is sort of like at each subgroup, what is that homology, and you can actually build such a map. So that's how you construct this D object. And then, as I said before, that allows you, the initialness here allows you to get a zigzag of weak equivalences, and therefore you get the uniqueness at the algebra level, and then translating back, you get the uniqueness at the level of spectra. So thank you very much.